Each day we're going to be learning one or two more basically tests for convergence. So everything we're doing is basically kind of building. So I did want us to like kind of keep in mind and review like each day we'll review all the tests that we have learned up until that point. For today we've only learned so far one convergence test, and that is the nth term test, which is really more of like a test for divergence because that's the only thing that it can show. We know that if the limit of the term is not zero, then that series for certain is divergent. If the limit of the term approaches zero, then we have no info. We don't know what that series is going to do. We don't know whether it's convergent or divergent. So today we are going to look at two series. We're going to look at what's called the geometric series and then the p-series, which will be one of those, like, if we get no information from the nth term test, it will be like an option that we could do to determine convergence or divergence. So again, today's notes, we're going to start off with the geometric series. And I did want to go ahead and define the geometric series for you first. So remember, when we say series, we're talking about the sum of a sequence. So literally, a geometric series is the sum of a geometric sequence, which technically geometric sequences were first taught in Algebra 1, whether you remember or not. Anyone remember what a geometric sequence would be? An example of a geometric sequence would be something like, I don't know, 3, 9, 27, but not that. Let me do math better. 18, 27. What's a geometric sequence? When you're multiplying. So a geometric sequence is basically when you're multiplying to go from one term to the next term. So a geometric series is where you're adding basically a geometric sequence. Since you're going to be multiplying by a term each time, all geometric sequences can be written in the form of a times r to the nth, starting at any number, and we're going to be doing infinite series. So that top part is going to be n infinity. A is going to be just some sort of constant that we have. Not necessarily the first term, but just some constant that we have. That R value does have a word. It is called the common ratio. And it's basically what we are multiplying by to go from term to term. And yes, when we first learned geometric series, like I think it was taught in Algebra 1, you talk about a geometric series in which you're multiplying or dividing to go from term to term. For us, it's going to be just easier if you think about multiplying going from term to term. So like this series, I'm going to put a plus sign at the end just to make it an infinite one. We can see that the R value we're dealing with, that is wrong. I don't know why I can't do math today. 9 times 3, definitely 27. Now that I can do math, that R value you're dealing with is basically a 3. And so things that we're going to be looking at when we're dealing with a geometric series, sometimes you will have it, written out as a series. Like if I think about another geometric series, I might have something like 1/2 plus 1/4 plus 1/8 plus 1/16. So being able to look at a geometric series when the terms are given, but then also being able to look at a geometric series when it's given to you in segment notation, and being able to recognize that's a geometric series. So something like 3 to the 1/5 of n. And being able to recognize that when we see this series, this is going to be a geometric series. Looking at this series, what number would you be multiplying by each time to go from term to term? 1/5. So like you can imagine, like your first term, n is 0, so you have 3, and then it'll be like 3/5 plus 3/25, and then that's going to continue forever. What's the easiest way to recognize that something is going to be a geometric series? Easiest way to recognize it is that n that we're dealing with is going to be in the exponent, and it's going to look like an exponential function. It may not look like a nice clean, simple exponential function, but in general, if it looks exponential, there's high likelihood that it is going to be a geometric series, and then it's going to be pretty easy to interpret. So when it comes to a geometric series, the way that we're going to determine whether a series is convergent or divergent. So we already have the nth term test, and the nth term test can only tell us whether a series is going to diverge. We do have some special types of series, and the first one is, of course, going to be geometric. And then that's going to lead us into, well, if it is geometric, then we are going to have basically a geometric series test. Do need to be able to recognize that it is geometric, so I'm going to kind of add this here. It's only geometric if it's in that format, and again, it has to be in that format for it to be geometric. And how we're going to look at it and what we're focusing on is we're going to look at the value of the absolute value of R. It doesn't need to be the absolute value of R. And basically, the absolute value of R can be three things, and those three things will help us determine whether that series is going to converge or diverge. So the absolute value of R could be less than 1, the absolute value of R could be greater than 1, or the absolute value of R could be equal to 1. The geometric series test can prove whether a geometric series is convergent or divergent. If your R is less than 1, are those terms going to be getting smaller or getting larger as you go to infinity? Smaller. So you're multiplying by a fraction, they're getting smaller. Those geometric series are going to converge. If R is bigger than 1, so those terms are going to be getting larger, that's going to be a geometric series that diverges. And if R is equal to 1, I'm just going to say that that is a weird series, and you're probably going to use the nth term test instead. It's probably going to diverge, but you wouldn't really use a geometric series, but it doesn't really make sense to just keep multiplying by 1. And when I say weird series, that might be a series that's like 5 plus 5 plus 5 plus 5 plus 5, or maybe something that goes like 5 plus -5 plus 5 plus -5 plus 5 plus -5. It's kind of a weird series, most likely diverges, but the nth term test will determine that, and not really the geometric series test. The geometric series is also unique. I put this reminder on here for me because I tend to forget talking about it when we have it. It is the only type of series where we can actually use a formula to figure out what that infinite sum is. So it only works, of course, if it does converge. If it diverges, it's not going to have a sum. But if it converges, then the sum of the infinite series is going to be equal to the initial term over 1 minus R. And again, that feels weird. I know that you're like, well, we're adding up an infinite number of things, but there are going to be times when we add up an infinite number of terms, it's going to equal a finite value. So we're just going to look through just some examples. Again, more often than not, a lot of these examples will have more writing than we're probably used to. So we have to make sure we perform clear and concise justifications. And I have just a few examples we'll look at. So yeah, let's go ahead and get started. So look at these first two. I have state whether each series converges or diverges. And then if it does converge, we're just going to go ahead and also find the sum. Like what would that series be equal to? And when you are looking for these, we're going to form our justification the same way that we did like the nth term test. So you're going to have to write down what you're considering, what that is equal to, why is it important, your conclusion, and then the name test. Well, first off, let's talk about these. Looking at these two problems, like the only thing I really changed was that bottom part in series, like where we're starting at. What is clear about that one of why I would want to use the geometric series test to justify conversion for that problem? It is in that form. Like it looks like an exponential, it is in the exponent. And I say that because eventually we're going to have like 6 different tests. We want to be able to recognize when is it geometric. And you're going to like it when it's geometric because those are going to be one of the easiest ones to identify whether it converges or diverges. So we see this as geometric, so we want to identify the absolute value of R. That's what we do for the test. What is the common ratio for this problem? what would you be multiplying by to go from one term to the next term? 0.25. So you write that down. Why is that important? Well, what is that number? Less than 1. If your common ratio is less than 1, what do we know that series is going to do? Converges. So I would have series converges, and then give the name test by, and you can abbreviate it, geometric series test. Is that second one with a different starting point going to have a different answer by any means? No, like it still has the same common ratio, so it is still also going to converge. So like the absolute value of the common ratio is still 0.25. Why is that important? Less than 1. So we know that the series converges by the geometric series test. Since it converges, we can actually find the sum. So again, to kind of explain what's happening here, this is a series. So like I could say, well, we have, this is 24, plugging in 0 first. So your first term is 24. And then basically you're dividing by 4 each time. So you have like 24 plus 6 plus 6 fourths plus 6 sixteenths. And that's going to last basically forever. But with the geometric one, we do have a formula to find the sum. What is the sum of those infinite terms? The sum is the initial term divided by 1 minus the r value. I could simplify it, but I'm just going to leave my answer like that. Same thing with the second one. It converges, so it has a sum. What will be the sum of that series? You have your initial term. This one is starting when n is 3. Divided by 1 minus the r value. Questions on those two problems? All right, let's just go ahead and move down to the next row then. Looking at this first one, I have the series starting at 1 to infinity of 5 to the negative n. I know it's the geometric series notes, but what about that one tells us or informs us that that is going to be a geometric series? It looks like an exponential. But if it is an exponential, so we do want to remind ourselves, the geometric series form in general is like this a times a common ratio to the nth power. Right now, this one is like 5 to the negative n power. So sometimes we have to use like some properties of exponents to rewrite it, just to make sure we identify the correct r value. What would be a way that we can rewrite this problem so it looks more like just something raised to the nth power? Moving to the denominator, what's your r value going to be? 1/5. So again, you can kind of see, and this is where just having just good properties of algebra, using those properties of exponents. 1/5 to the n is the same thing as saying 5 to the negative n. So then what do we need to identify? We have to identify the absolute value of the common ratio, which is 1/5. Why is it important? That's less than 1. Since it's less than 1, we know that this series converges by the geometric series test. We could find the sum. What will be the sum of it? So we have our first term, plugging in 1 for n, divided by 1 minus r. Again, could leave your answer as that. I am just going to kind of simplify this one because I think it's nice how it simplifies. So we get 1/4. And again, I like finding the sum for the geometric one. I know it feels weird. You're literally adding up an infinite number of terms. So we have like 1/5 plus 1/25 plus 1 over 125th going on forever. Adding up those infinite fractions, we are going to get just 1/4. I do want to talk about this one just to kind of show you what would be required. If you're justifying your answer, you would only have to show that statement. Showing how you rewrite it is optional. Because again, you're going to be doing so many of these, like hopefully you can look at that problem and just see what the R is, and you wouldn't have to rewrite it on paper, but of course, rewrite it if you need to. But if you can correctly identify the R value without rewriting it, there's no need to actually show that work on paper. And then looking at this last one, similar to integrals, we know that for an integral, we can kind of split up and deal with each term separately. Same thing with a series. If you're looking at a series, you can split split it up and deal with each term as a separate series separately. So if I'm looking at this one, this is a series created by this expression, and that is giving you a single term. So like we plug in 0 for n, that would be your first term, plug in 1 for n, that would be the second term, etc. The way that you have to justify this one is, again, a lot of this unit is just making sure we justify correctly, is we're going to have to consider the two series that creates that one, prove that those two series are either convergent or divergent, and then use that to talk about the original one. So what do I mean by that? The first series I'm considering is this one. The second series I'm considering is that one. And I'm going to treat them separately. Yes, it's obnoxious to do all the extra writing, but again, we have to make sure we justify this formally and correctly. Looking at this first series, again, what is the absolute value of r? Absolute value of r is 0.25, which is less than 1. That's why it's important. So this series is going to converge by the geometric series test. Then for the other one, what is the common ratio? It is 0.5. Why is that important? Less than 1. So that series is going to converge by the geometric series test. Well, if both of those series both converge, what can we say about the original series? We can say that the original series also converges. What would your answer be maybe if one converged and the other one diverged? You would know. What would it do? If one converged and the other one diverged?
Diverge.
You can't have one part diverging and expect it to converge eventually. So both converge, then the whole series is going to converge. If one, or of course both diverge, then the original series would diverge. Last example with geometric series test, and then we will do the P series. Try those two for me. And again, making sure you write the correct justification, which would include identifying the R value. Maybe you need to rewrite it to identify the R value, stating why that R value is important, and then drawing your conclusion from there. And again, if you can identify the R value without rewriting it, that's fine. I'm going to rewrite it and trying to make the R value clear. Of course, we'll do all these without. And both of these are geometric series. If they weren't geometric, then obviously we wouldn't be able to use this test. Looking at this first one, this is the series from 1 to infinity of 6e to the n over 4n. If I want to think about this one as a geometric series, that's the same thing as 6 times e over 4 to the n. That way I can kind of clearly see it as that a times r to the n formula. So identifying the absolute value of r, the absolute value of r is equal to e over 4. E is a constant, about 2 point something, so I have 2 point something over 4, which is going to end up being less than 1. So series converges by the geometric series test. If I want to find the overall sum again, I want to find the first term, so when n is equal to 1, divided by 1 minus the r. So again, that series does converge. What does it converge to? It converges to that number. That is the sum. Here's another one. We want to verify that it is a geometric series, but we do have a list of terms. What is the R value that you're using to go from term to term? Try again. What are you multiplying the numerators by? 2, where you're multiplying the denominators by 3. I also see this as changing from plus minus with your R value technically, negative 2/3. Still geometric, you're multiplying to go from one term to the next. So justifying your answer, what's the absolute value of R? 2/3. Why is that important? It's less than 1. So that is going to converge by the geometric series test. Could find the sum of it. So like if I just want to add up all those numbers, what would it be equal to? The sum of those numbers would be the initial term over 1 minus the common ratio. Questions on the geometric series? All right, so that is the geometric series. The next one that I wanted to cover, so I didn't originally want to cover it today, but tomorrow is a short day, so I'm going to adjust my notes a little bit, is going to be the P series. So this is going to be in the next section of notes. I do think it's also beneficial to teach it today because the P series is going to look very, very similar to a geometric series. And in fact, students often mix them together, and so it is kind of good to be able to see them differently. The word P, it gets the same P series. P basically stands for like a power. So a P series is going to be a series that can be written in this format. So again, we're still looking at an infinite series. And it's going to be A over N to the P. And P in this case is a constant power, basically. And that's why we're calling it a P series. Many students confuse these with geometric because in many ways they do look geometric. You're just kind of first looking at them. An example of a P series, if I were to make up a few, what's one I want to make up? We'll say n is equal to 1 to infinity up to over 3, nope, n cubed. That would be kind of more obvious of a P series. Looking at what that generates, just to kind of write out some of those terms. So I have 2 over 1 cubed plus 2 over 2 cubed plus 2 over 3 cubed, and I can of course keep going with this. So looking at those terms, people might look at that at first and it says, oh, that looks geometric, but then you quickly see that you're not multiplying by the same number in the denominators. It's kind of like the denominators are raised to a power. And so that is what we're going to look at for a P series. Again, big kind of comparison for them. If I go back to the geometric series notes, the geometric series, the n is in the exponent, so it's an exponential function. For a P series, the n is being raised to a constant power. So that's what we're going to kind of keep separated. So when we identify that we have a P series, we are going to basically use the P series test. When is the P series test used? It's of course used when you have a P series. And we're going to look at P. So similar to a geometric one, where we look at a common ratio, for a P series, we are going to look at P. Similar to the geometric one, P can be several things. P can be less than 1, P can be greater than 1, or P can be equal to 1. But you want to be careful. When the P series is going to converge and diverge, it's going to be opposite in some ways of the geometric one. So you want to think of which one's going to make the terms get smaller. Well, P is a power in the denominator. If P is less than 1 or greater than 1, which one would end up having the smaller terms as we went out to infinity? Greater than 1. So you're thinking which one would have the bigger denominator, so that's going to be the smaller number. So when P is greater than 1, that P series is going to converge. When P is less than 1, that P series is going to diverge. When P is equal to 1, that is also going to be a case when it diverges. It's actually a special type of P series called the harmonic series, which we'll talk about a little bit later. But it is a very special type of series that has a name. It is actually related to music, which is why it has that name, harmonic series. but it is going to always diverge. How we justify it, again, very similar. We just have to kind of recognize that we have a p-series and then justify the same way. Like identify what's important, say why it's important, draw your conclusion, and then say the name test. P-series, you can also abbreviate PST. So we won't abbreviate all of our tests, but P-series is one of them. So example, let's look at these two. Try both of those before I go over them. And be careful, one of those is geometric and one of those is a p-series. Try both of those for me. And so like when we're looking at these, you'll notice that these problems for the most part like are not difficult yet, but like if you don't know the test and you don't justify them correctly, that's really where kind of the issues are arising from. As you're looking at both of these, which one is going to be the geometric one, and how can you easily tell? The first one is the geometric one. What's the big clue that it's geometric? And it's in the exponent. So again, I would probably rewrite this one. You can definitely identify the R value correctly without rewriting it, as long as you say the R value isn't 3. Technically, if we're rewriting this one, this is the same thing as saying 2 times 1/3 to the n. So that's just kind of making sure we're clear with your R value. So this one is geometric. So again, we're going to state what's important. So R is equal to 1/3. The absolute value of R, to be clear, is 1/3. Why is that important? It's less than 1. So what do we know about that series? Converges by the geometric series test. The instruction,
Mr. Brown, how did you?
you know how? So this is a geometric one. We do have a sum formula. The sum of a geometric series is the first term, which in this case would be 2/3, divided by 1 minus the common ratio. Looking at that second one, clearly that first one was a geometric one, but why is that second one kind of clearly our p-series test? N raised to a power. So again, similar justification. P would be equal to 3. Why is that important? That is greater than 1. Since P is greater than 1, what can we say about that series? Converges by p-series test. And again, the way I kind of keep those separated, both of those series are going to converge if the terms are going to get to be very, very small, very, very quickly. So like for a geometric one, you want to be multiplying by a fraction to get those terms to be small. For a p-series, you want that denominator to get very large, so that overall fraction becomes very small, and then it will have a sum. There is no formula you have to know to find the sum of a p-series. Like it does exist, you're welcome to look it up, but it's not one that we need to know how to do. Go ahead and try these last 4 for me. Of course, you always want to ask yourself if you are dealing with a p-series. Because again, if it's not, then you might want to use like the inter-term test to prove divergence, or geometric series test if you're dealing with a geometric series. And again, for that second one, you would want to kind of split it up and justify each term individually, and then say what's happening overall. And again, the most annoying part, I think, with this unit is not right now like the math. It's just the writing and making sure you justify something correctly. But this is where we're going to stop at. So there's my answers for those four. Again, geometric and p-series are going to be the really easy ones to deal with. You just have to identify a value. That first one, your p-value would be 1/2. That's the exponent we see in the denominator. P is equal to 1/2, which is less than 1. So p-series diverges by p-series. So series diverges by p-series test. The second one, you would want to rewrite and consider those two integrals, those two series separately. The first one, p is 2, which is greater than 1, so that first series is converging. P is equal to 3, so series is also converging by the PST. Therefore, if both of them are converging, then the original series is also going to converge. And then looking at that second row, it's not in that sigma notation, so you would have to identify what that p-value is. Do be careful, a lot of people see fractions like that, and they want to force it to be like a geometric one. But moving from 8 to 27 to 64, you're not multiplying by the same number each time. So you want to see if it's a p-series one. And it is. Those denominators are basically numbers being raised to the third power. So p would be equal to 3, greater than 1. So we know that series converges by the p-series test. Questions on those first three before we do that last one? All right, and then the last one is kind of a weird one. Two ways to justify it. The first way, p would be equal to 1. That's the exponent that you see. What is important about 1? Like, I know it looks weird right now, but we're going to say that p equals 1, which is less than or equal to 1, and that's why the series diverges. That feels weird, right? So the better way to do it is the harmonic series is going to be a series that we can memorize and say diverges without justification. So if you see the harmonic series, you can just state the series is harmonic, so it diverges without justification. It's considered one of our principle, if you will, series where we don't have to ever justify our answer. And we'll have 3 series where we won't have to justify. We have the harmonic, the alternating harmonic, and then the canonical series. Right now we're just at the harmonic one. Never have to justify it. It is always divergent. Questions on those problems? All right, so that's where I'm going to stop today's notes at. We will do the integral tests tomorrow. Remember, you do want to keep track of all of these tests that we're doing. So if you're looking at the top of the calendar, like I have just the blank version of all these tests, you want to fill it in as we learn them each day. Or there is also one filled in underneath it. We'll know all of these eventually, but it's going to be something you want to kind of keep referring to because you do have to know these series. You have to have it memorized of when to use them and then the conclusions for them. As we progress through this unit, we'll start seeing more and more of them mixed together, just to kind of force our brains to switch between a geometric, a p-series, and then all the other ones that we have to learn. Homework-wise, what I want you working on, if I go back to, I'm going to go back to here on the calendar. So the homework I'm assigning right now is going to be just homework 2. I'm going to be completely honest. You should be able to finish homework 2 during class time. And that way, homework 1 and 2 should both be completely done before tomorrow. You're more than welcome to start homework 3, but do realize we still have to learn the integral test, which is kind of mixed in with some homework 3 questions. So if you did want to get ahead, I guess you could look at some at homework 3 and just pick out the ones that are p-series, so you should be able to identify those fairly easily. But again, the geometric series homework can go by real fast. You're just identifying the R value and then practicing writing those justifications. So we're going to do the integral test tomorrow. And then on Thursday, we're going to do the direct comparison test and the limit comparison test. And that will put us at halfway through the first half of the unit, if you will. So I can go ahead and get started on that homework. Again, this is the 1 unit. I'm going to ask you